Okay, so now we are going to see how we can compute parameters of linear regression analytically. This is probably the most technically challenging part of the lecture and probably the longest, but I hope it's not going to be so bad, because this is stuff that you are more or less familiar with from regression analysis. So first of all, how it looks like, right? So if we fit a linear regression with one response variable and one predictor, then it means that we are minimizing the sum of squares of these like vertical distances from our points to our regression line. With two predictors, we are also minimizing these vertical distances, but now instead of a regression line, we have a regression plane. So for p predictors, we have like something like well, hyperplane. Yeah, it's called a hyperplane. Yeah, so with p predictors, we would fit a hyperplane. So one predictor line, two predictors plane, p predictors hyperplane. Now, suppose that the true model is a linear model. So if we have some estimates for regressed parameters, then we can make predictions according to this formula. So given, well, a new data point, so given a new data point that was unobserved before, this is how we make predictions. Now, so the model parameters are chosen to minimize the residual sum of squares, right? So the residual sum of squares is often also called the loss. Well, the loss function is a more generic term. So the loss function is like any function that we want to minimize in order to fit our model into observed data. So residual sum of squares is just a particular case of a loss function. So sometimes we use the mean squared error, which is really just the same thing divided by n. It doesn't matter, of course. So now, how can we minimize it? So look, this is a function of several variables, beta 0, beta 1, and so on, beta p. Now, in order to find the minimum value of any function of several variables, what we need to do, we need to find its derivatives with respect to these variables and equate them to 0, right? So let me do this. So what is the partial derivative of L with respect to beta 0? So we're going to just take this expression and differentiate it with beta 0. So first of all, this is the sum. The derivative of the sum is still the huge sum of derivatives. So this is going to be the sum from 1 to n. Now we are going to differentiate the square. So when we differentiate the square, we do 2 times whatever is inside the square is yi minus beta 0 minus this sum xij beta j this is the j from 1 to p. Next, we need to multiply by the derivative of whatever is inside the square with respect to beta 0, and that's minus 1, right? So I'm going to just write 1 in front here. Okay, cool. Now, in the same way, we can write the derivative with respect to beta j, where j is not 0. So let me do it too. So probably let me do it somewhere here. So dl d beta j. So here I'm assuming that j is not 0. The first part of the calculation is still the same. It's still going to be minus 2 times the sum by I from 1 to n capital of the same thing, y I minus beta 0 minus the sum j from 1 to p of x I j b j. But now we need to multiply by the derivative of this with respect to beta j, and this is again the huge sum. So when we differentiate with respect to beta j, So terms that do not contain beta j are going to vanish. So only beta j itself is going to remain there, and the coefficient is xij. So I'm going to do times xij. Okay, so this is how we can derive the partial derivatives of our loss function with respect to parameters of the model. So in the matrix form, it looks like this. Well, what does it mean? So let's figure it out. So first of all, what are these? So y here is a column vector. So this is like y1, y2, and so on up to yn. Now beta here is also a column vector. So beta is our beta 0, beta 1, and so on, beta p. So they have different sizes. Notice that y is n by 1 vector and beta is p plus 1 by 1 vector. Now x, so recall that x is all our training set observations, so I'm not going to write them down. So x is like a huge matrix, and x has n rows and p plus 1 columns. P plus 1 columns. Okay, now let me write it here. So y is n by 1. So x is n by p plus 1. So beta is p plus 1 by n. So which means that x beta is now going to be, well, sorry, beta is p plus 1 by 1, right? So x beta is going to be n by 1. Now we can subtract y minus x beta, n plus 1, n times 1 minus n plus 1, and n times 1. So this, okay, so let me erase this. So I think it's going to be easier to see. So now we see that this y minus x beta is actually n by 1 matrix. Well, but the first term here is the same thing transposed, which means it is 1 by n. And the product of 1 by n and n by 1 is just 1 by 1 matrix, and it is a scalar. And if you check it, you will see that this is actually just the residual sum of squares. This is our loss function from the previous slide. Only it is kind of written in the compact matrix form. Now, it goes further. So if we now want to write partial derivatives with respect to beta, now recall that our beta is actually is a column vector, right? So it's beta 0, beta 1, and so on up to beta p. Right? Now, which means that beta transposed is a row vector. So beta 0, beta 1, and so on, beta p. Now, what is this? The residual, the partial derivatives of residual sum of squares with respect to beta transpose. So this is nothing else as just derivatives of our loss function with respect to beta 0, beta 1, and so on, beta p. Well, this is a matrix equation, and you can check that it actually yields the same result as we saw 2 slides before. So these scary-looking huge equations. But let me just give you a little bit of intuition behind it. So why does it work? So basically, it works because our residual sum of squares, our loss function of beta, right? So from the previous slide. So y minus x beta, right? So y minus x beta transposed times y minus x beta. But this is something like, it's not exactly, but it is something like y minus x beta squared. And when we differentiate it with respect to beta, we're going to get 2 times y minus x beta times the coefficient at beta, which is minus x. And this is what we get here. So only, since this is matrix calculus, we really probably need to first derive like theorems about it. But it's not my primary purpose to derive these theorems. So rather, I'm going to give you a bit of intuition behind it and how you can write it nicely in compact form and remember what it means. So basically, in compact matrix form, it works because all dimensions are consistent with each other, and because rules for matrix calculus are somewhat similar to rules for usual calculus. Okay, now to find the point of local minimum, we equate all partial derivatives to 0, right? So which means these are our partial derivatives. We need to equate them all to 0. So remember that this is actually a matrix P plus 1 by 1 matrix. Well, you probably want to conclude that, you know, we have 2 terms, we multiply 2 things here. So the product is 0, which means that either the first of them is 0 or the second one is 0. It doesn't work for matrices, right? So we cannot do it like this for matrices. So instead we have to convert it to a system of equations like this. So first we can just erase 2 because we can always cancel by 2. It's just a constant. So the remaining equation is minus x transpose y. Minus and minus gives us plus plus x transpose x beta is 0. So then we are going to move it to the right hand side. So x transpose x beta equals x transpose y. And now let's think a little bit. So let us look at this matrix in front of beta here. X transpose x. Now our x is a super huge matrix, is our whole training data set, and it is very, very tall. It has a lot of rows and maybe not a lot of columns. So it looks like this. The transposed version of x is very, very wide and not very tall, right? So when we so this is p plus 1, this is n, so this is n, this is p plus 1. The product of them is actually quite a, it should be a matrix of the size p plus 1 times p plus 1, right? So this is really just a small square matrix, p plus 1 times p plus 1. So this is our x transpose x. But in that case, if it is a small matrix, we can hope that it is invertible, right? So we can just multiply this equation by x transpose x inverse. And by multiplying this equation with x transpose x inverse, we just find the answer. Now, in order for this to work, x transpose times x should be invertible. This is very important. Now, there's more to the story, because to ensure that this is actually a local minimum rather than a local maximum, we need to find the Hessian matrix, so the matrix of second partial derivatives, and we need to show that it is positive semi-definite, which means we need to show that so all eigenvalues of the Hessian matrix are non-negative. We're going to do it in tutorial, not here. So here, let me just explain a little bit elaborate on this matrix and what may go wrong with it. So what is this matrix again? X transpose times x. Now, this is the product of the transposed x and original x. Right, so this is x transposed This is X. But generally speaking, how do we find the product of two matrices? So every entry of the product of two matrices is a dot product of a row of this matrix and a column of this matrix. But every row of X transposed is just the same as a column of, so rows of X transposed are the same as columns of X, is the definition of transposed. So it means that entries of this matrix, X transpose X, are just dot products of row of columns of X with themselves. So entries are like columns of X I dot product with column of X J. So the dot product of two columns of X. So in other words, we have a few columns of X that can be thought of as vectors in the space Rn, and we take pairwise dot products between them. So this construction, so when we have several vectors and we take pairwise dot products of these vectors and form a matrix, is called a gram matrix. Gram matrix. And there is a theorem in linear algebra that a gram matrix is always positive semi-definite. So notice that in order to show that we have a local minimum, we want to find a Hessian matrix and show that the Hessian matrix is positive semi-definite. So here we're talking about something else. So about the gram matrix, and the gram matrix is always positive semi-definite. So maybe it's a hint how to prove that the Hessian matrix is positive semi-definite. In any case, what I'm trying to say is that another fact is that the gram matrix is invertible if and only if the vectors involved in its construction are linearly independent. So in other words, what we see here is that the matrix X transpose X is invertible if and only if columns of the matrix X are linearly independent. So this is going to be important later, but now let's see that, in order to construct predictions for the training data, we just need to take X times this beta hat is the value of beta that minimizes the loss function. So is the arg minimum of the loss function. And the loss function is in turn the residual sum of squares, right? So now this matrix that comes in front of Y to construct predictions is called a hat matrix, well, because it puts a hat on X. That's a bit of a statistical joke. Now, so finally, as we already saw, that linear regression doesn't work if columns of the matrix X, if columns of our training data are linearly dependent, right? Because in that case, X transpose X inverse is going to be undefined. So if columns of X are linearly dependent, then X transpose X is not invertible. So now, if you think a little bit about it, then columns of, well, this matrix X is filled with random numbers, and usually random numbers do not happen to be linearly dependent. So there are two typical situations when this occurs in practice. So one is if we have too many predictors, right? So originally X is supposed to be like this, is very, very tall and very narrow matrix, right? So n by p plus 1. But if we have too many predictors, then it actually looks different. It looks like this, right? So we have just a few observations, but a lot of predictors. So this is p plus 1, and this is n. And if that happens, then of course we just have too many. We have more than n vectors, each of the size. We have too many vectors, and if we have too many vectors, they are always going to be linearly dependent, right? So in practice, this kind of always occurs with genomic data. So here is a small example of real genomic data that I worked with some time ago. So these are genomic data of NTU students from the School of Biological Sciences. So if I have 26 students and 3,000, I think this is called nucleotides or something. So observations of some genomic variables. And this is a pretty typical example. So then the number of observations is just 26, and the number of predictors is 3,000. So it by far exceeds the number of observations. So in this case, we cannot do linear regression at all. It just doesn't work. So the solution to this is regularization methods, and the plan is to do it in lecture 4. So eventually you will learn how to deal with this. So another typical situation occurs when we convert categorical data to numeric data using dummy variables. So here is a typical example. So data of Titanic passengers. So every record here is one person. Sex has 2 values, male and female. Embarked has 3 possible values, depending on the port of embarkation. So Sherbrooke, Queenstown, Southampton. Now, in order to use this data in statistical modeling, we convert them to dummy variables, like this. So we just zeros and ones. Yeah, but now by construction, if say you take C plus Q plus S, the sum of these 3 columns, then by construction is always going to be just all 1, 1, 1, 1, 1, right? So the sum of these 3 columns is just the column of all ones. But again, by construction, the first column of our X is all the ones. So which means that if we do this, if we encode categorical variables with dummies, then our matrix X always is going to have linearly dependent columns, and linear regression will break. So, but the solution is very simple. So we just need to remove the last dummy from each categorical variable. So if our categorical variable has k different values, then we should have not k dummies, but k minus 1 dummies. Like we do not encode male, so we just have the variable female. So whoever is not female is going to be male. That's the idea. So we do not encode Southampton. So whoever is not C or Q is going to be S, right? So we just are going to remove them from X, and then we're fine. Okay, so let us look again at the formula for linear regression and write out dimensions of the matrices involved, right? So X, so recall that X is n by, so Y is an n by 1 matrix. So what is X? So X itself is n by p plus 1. So X transpose is going to be p plus 1 by n. Now, X transpose X. So X transpose, as we know, is p plus 1 by n, and X is n by p plus 1. All right, so which means that X transpose times X is going to be p plus 1 times p plus 1. Inverting the matrix does not change the dimension. Of course, it's still going to be p plus 1 times p plus 1. So when we take the product of all these matrices, the end result is going to be just p plus 1 by 1 matrix, right? The end result. But while we are calculating it, so we have to deal with some pretty huge matrices. So this matrix, this matrix, and this matrix are pretty huge, right? So my point being is that if n and p are large, then this calculation involves the product of very large matrices, and it could be, sometimes it could be numerically unstable or just slow. And in that case, instead of using this direct formula, sometimes under the hood, people use some other methods, some versions of gradient descent that we are going to get familiar with in today's lecture just a little bit later. Okay, and finally, So I hope you were able to sit through the whole chunk of the lecture. Sorry, it was a bit too long, but that's the deal. So now please answer this quiz.